Okay. Can you see my screen? You can say something.
Yes, we can see your screen.
Very good. Okay. So last time, where was it? There it is. Okay. So we completed the discussion. Make some more space around here. Sorry for that. So last time we completed the discussion about vectors and tensors in curved spaces. Again, this is particularly important for us because, as we say, the space-time that we're working is curved. And the important takeaway message was that we treat vectors as directional derivatives. This is what enables us to generalize the concept of vectors into non-flat spaces. That will enable us, that's what we're going to do now, to transport vectors along curves from one point to other curve, from one point to another point, because as we said, vectors belong really to the tangent space at a given point. So because of that, we have to add this concept of directional derivative so that we'll know which direction the vectors will point into. And then we discussed covariant derivative, generalization of standard derivative, of partial derivative, sorry, into curved spaces. The advantage is that it reduces to partial derivative in flat spaces, namely in the absence of gravity, and that the outcome is a tensor by itself. So we using covariant derivative, we can write down tensorial equations, which is what we are after. And then the last time we did was giving a geometrical interpretation of covariant derivatives. We explained what it really means and why do we have to have this extra affine connection, because as we said, when you take a derivative of something, right, so you have a vector, at a point x alpha, and we want to take the derivative of the vector. What we really do, we're doing two things, right? So we look at the vector at another point nearby, x alpha plus bx alpha, and now the vector will be different, right? Let's say this will be the vector, and since we cannot directly compare, so this will be v at x alpha, this will be v at x alpha plus bx alpha. So in order to be able to compare the two vectors, we must first go back, take this vector going back, transport it back to the original point in a way which is parallel to itself. So that is why it's called parallel transport. So this is v transported at x alpha. Only at the second stage, we can use this parallelogram rule, namely taking the difference between those two, delta v alpha. Right, and so we really, without even saying that, when we take a derivative, we have to take two steps. And it is the first step that can cause the vector to change, because the space itself may change from point x alpha to x alpha plus bx alpha. Of course, we do not see that in flat spaces, but when the places are not flat, then we do see it, and that's the origin of this extra affine connection which appears inside the covariant derivative. We then show that another way of describing a geodesic is a path, which is of course the shortest path between 2 points, but it is also a path in which the vector tangent to the curve is always parallel to itself along the path, right? And then we extended the definition, extended the discussion to discuss gradients, divergence, and curl in curved spaces. You have seen that. I believe you have seen that, right, in several specific examples, such as curvilinear coordinates, maybe spherical coordinates, or cylindrical coordinates. But now, of course, what we do is much more general. And of course, what you know is specific examples of the thing that we're doing here. Any questions before we move on to the next part? Any questions? I postponed the problem set until today, so you will get the new problem set today. And I'm discussing with somebody who's grading your problem set. We'll see how this goes. Okay, so today we begin a new chapter. It's not a very long one. I think it will take us something like 2. I hope not more than that lectures today and on Sunday. Maybe we'll meet some Thursday for that. And that's called curvature. That's the last big mathematical subject that we have to go through before we go to the more physical part of this course. So if you are feel a bit shaky with the math, then whether it encourages you or not, we only have like a few more lectures with main math before we go back to discuss a lot of physics. So the title is curvature. Okay, so remember the big question that we're after, right? We had 2 big questions. One is how do particles propagate? How do they move in the presence of gravity? The answer is along geodesics. And that's true for free particles, of course. The second question is how does the existence of mass or energy act to curve space-time? So how do gravity curves the space-time? It's a big question. But, even before that, we must be able to answer an even simpler question, which is, what does it mean, a curved space-time? How do we know that the space-time is curved rather than flat? The second question is, how do we know that the space-time is curved? Right. So what we're really after is some, mathematical description of a curvature, which, does not require us to look at the space from the outside. Again, so you can say that the surface of the Earth is round. And how do we know it's round? Because we send an astronaut or we send a satellite and he took a picture of Earth and we see that the Earth is round. Now, that's not what we're looking for. We're looking for a way of knowing that the Earth is round and not flat without leaving the surface of the Earth. And if you're thinking of that, so not just without leaving the surface of the Earth, it's also without looking at the surface of the Earth as a 2-dimensional space embedded within a 3-dimensional bigger space, right? That's what an astronaut does, right? And we want, assuming we are 2-dimensional creatures, we want to know that the space that we live inside is curved rather than flat, without leaving it, without having the ability to look from the outside into it, right? And of course, there is a way. Some people, for unknown reasons, still don't believe this, but that's not my problem. Not my immediate problem, at least. And if you think that the surface of the Earth is not particularly interesting, you think about the universe as a whole, right? There is no way for us to leave the universe that we live in and look at it from the outside, from a different universe or something, higher dimensional universe that may or may not exist. We want to be able to tell whether the universe that we live in is curved or flat without having the ability of leaving the universe, right? So, of course, there is a way, and the way was found initially by Gauss, the great mathematician of the 19th century. And that's what we're going to do now, to learn this way, how to, basically answering this question, how can we tell that the space-time is curved? So for that, we need to have a proper definition of what we call a parallel transport. Which is exactly what the last thing that we touched upon in the last lecture. So, okay, remember again, when we had the flat space, right, we didn't really have to be careful about moving a vector from one place to the other, right? So if we have a flat space, right, then we had a very natural way of comparing vectors in two different points, right? Because if we had a point, this is my space, right? X and Y. I have a point P. I have another point Q. Right, now I have a vector at point P. Right. Now I can take a path, whatever path I have, doesn't have to be the shortest path between point P and Q. And I can always take my vector P and transport it along this path while keeping it parallel to itself, right? It's kind of, I'm carrying the stick with me and I just move it parallel to itself. Till eventually I reach Q. Right. And when I reach Q, now I have the same vector, it's in Q, and now I can compare it to another vector that may be in Q. I can take the difference between them. I can do whatever I want to do. Is that thing. Now, the concept that I used was, moving the vector V. Sorry, use a different color. I was able to move the vector V from point P to point Q while keeping it parallel to itself. Essentially keeping it constant. And the reason is that, if I were to choose a different path, I could choose this path, and I could move the vector V along this second path, right? So this would be path B, this would be path A. If I were to move it along path B, I would get the same result when I get to Q, right? It doesn't really matter which way I choose. In flat space, I always end up with the same vector when I reach Q. Okay. So the concept of moving a vector from one point to another while keeping it constant, that's what parallel transport. So this concept, maybe I should write it down, right? Moving a vector along the path while keeping it constant. Is known as parallel transport. you know, and it's very natural. It's so natural that you've actually been doing that all along. Every time you did any vector analysis, and you didn't really ever have to pay any attention about that. Right? Yeah, guys. At least you don't say anything, and I don't know if you're with me or if I'm going going too faster than that, or should be going no. don't dare you. Yeah, okay. Okay. Of course, the one thing which is needed to get a parallel transport is that we are able to, you know, construct a path between point P and Q, so they are connected somehow. Right? If they're not connected, if they live in two different universes which are not connected, we cannot form a path between them. So we cannot do this parallel transport. Okay. Now, what about non-flat spaces, like general spaces, or curved spaces? So now let's look at curved spaces. Can I do a parallel transport of a vector along a curved space? Or inside a curved space? Not a tricky question. Can I do that? Yeah, guys, it's a question for you. Huh? Can I do? Yeah, right. So let's say this is the surface of a sphere. Right? I have a vector, point P here, and I have a vector along the surface of the sphere. Right? Can I parallel transport this vector to any other point along the sphere? Yeah, of course I can. Right? Nothing prevents me because locally it always looked like Euclidean. But what's going to be the difference between a curved space and a flat space in that respect? Now, guys, what will be the difference between a curved space and a flat space here? Any suggestion?
Maybe it's depend on the path you choose.
Exactly. So if I transport my vector from point P, let's say to point Q, right? Now the outcome does depend on the path. So for example, if I take this path here, so let's say that I'm going from the equator to the North Pole, right? I take my vector with me and I carry it with me, right? And I just go along, and go north, right? So the vector will be going like that, like that, like that. I reach a North Pole, it will be like that. Legitimate, there's still a vector, it's parallel transported to itself. But now I can choose a different path, right? If I go along the red path, I go along the equator and then I go north, right? Then I carry the vector with me parallel to itself along the path. Right. So the the sad fact is that there is no, the outcome of the parallel transport from point P to point Q depends on the path that we choose. There is no natural way, maybe I should say that, right? In the curved space, the results of a parallel transporter a vector from one point to the other depends on the paths taken between the points. Right? So there is no natural way of uniquely move a vector from one point to the other. Right? We can always do a parallel transporting, there's no problem, right? But the results depend on the path. Now, sadly or not, this is an inherent problem. There is no way of solving this problem. It's just there. Right? There is no natural way to uniquely move a vector from one tangent space, like say TP, to another, say TP. Right? Now, this actually have quite interesting consequences about physics when you think of it. For example, when we compare velocities, we can only compare the velocities of two particles at the same time, at the same point in space. Right? The relative velocity between 2 points, 2 particles which are at the same point in space, we can measure that. Right? This would be always smaller than the speed of light, but it will get some value, right? But we cannot really measure relative velocity of points which are in different locations in space, right? The classical example is what we know, the cosmological redshift, right? We say that galaxies recede away from us, right? So we're basically saying, oh, the galaxies are, Hubble's law, right? So the galaxies are moving with respect to us. Now we cannot measure the motion, they're not here. And they're not really moving with respect to us. What happens to these galaxies, by the way? Why do we see them as moving? Do you have any clue?
The space between us is expanding.
Right. They met well, and now let's say it in a more physical way. The metric is different. Right? The metric that was by the time that these galaxies emitted the photons that we're seeing is different than the metric it is right now when we're observing them. Okay, think of that. It's a bit of teasing you. We will discuss these things properly in due time. Right. If you simply think of it in terms of galaxies being moving away from us, you end up with contradiction because you'll find out that some of these galaxies will be moving away from us at speeds which are faster than the speed of light, which is of course not true. Okay, we'll get to that. Okay, questions about that before we start digging into the math? Any questions? No, nothing. Okay, so what, a parallel transport is really the, curved space-time generalization of the concept of moving a vector while keeping it constant, right? As we move it along the path. So of course we're going to generalize that to tensors of any arbitrary rank. So parallel transport. This is the curved space generalization of keeping the vector constant while moving along the path. Right. So let's say that we had some vector and it's a flat space, right? So this is a flat space. We choose a path, right? Specified by lambda, right? Now we have and we want to have a vector which we keep it constant. So what does it mean we keep it constant? So we have the curve is specified by the coordinates x mu of lambda, right? Lambda is the parameter along the curve, right? 0, 1, 2, 3, 4, whatever, right? The coordinates are specified as x mu of lambda, right? And what do we mean that the vector is so in flat space time? What do we mean by saying that the vector is kept constant? Right? And we say or tensor, right? Doesn't matter. So keeping a tensor constant, keeping a tensor constant, right? T constant just means that dt over d lambda, which is what? Dx mu over d lambda dt over dx mu is equal to 0, right? The tensor or the vector, again, it's flat space-time, so it's easy to visualize, right? I have a vector, right? The change in the vector as it moves from along the path lambda is 0, right? But really I'm taking the derivative with respect to the coordinates, and the coordinates themselves change with lambda, right? It's a definition of a path. So how do we generalize that? Very easy. What is the obvious thing to modify here?
The derivative?
Of course, right? The derivative. What are we going to do?
Make it
Covariant.
covariant.
Covariant, exactly. Very simple, right? So, so to make this a tensorial quantity, so to make this a tensorial quantity, right? We define definition a covariant derivative along a path. Right? Or in other words, is directional covariant derivative. Sometimes you find that in textbooks. Directional covariant derivative. by the operator, which I'm going to mark as capital D, D over D lambda, right, is what's in here, dx mu over D lambda times nabla mu. That's the definition. Now, the definition of a parallel transport. Right, of vector v along the path x mu lambda. Right. What will be the definition of that? How would I define a parallel transport?
Directional derivative is 0.
Exactly. Very good. You said that?
Me, hi.
Hi. Say your name, that's easier.
Ah, David. Yeah.
Small. Right. So it's just d v mu over d lambda. Not sure where to put the parentheses here, right? It's just dx sigma over d lambda and another sigma v mu, or dx sigma over d lambda v mu semicolon sigma. Or if you really insist, this would be d v mu over d lambda plus gamma mu sigma rho dx sigma over d lambda v rho is equal to 0. This is the definition of a parallel transport. We're taking a vector and we keep it constant, not changed. As it moves along the path lambda, general path, not necessarily a geodesic. Now, of course, now we can do the same immediate to generalize to any tensor of any rank. Right? So for any tensor, right? Parallel transport of the tensor. E over d lambda of t. And mu1, mu n, mu1, mu L is just dx sigma over d lambda, right? And then the covariant derivative of the tensor has to be equal to 0. By the way, the book by Sean Carroll uses slightly different notation for covariant derivative. He uses d over small d. Carroll's notation. But interestingly, in different textbooks, you find different things, different notations. Not sure why is that. I'll just stick to this one because I think it's easier to discriminate between covariant, between this and other methods, other notations. So, for example, right, if we take the 1,1 tensor dt over d lambda mu. Of course, this would be dt mu over d lambda plus gamma mu sigma rho dx sigma over d lambda t rho nu, and then it will be a minus gamma. Let's see, what will be the indices? Okay, so that means indices mainly rho sigma nu x sigma over the lambda to right? Do yourself a favor and follow all the indices. Make sure that everything is clear. Right? So these equations, you know, this one, equal to 0. And these ones, these are known of equations of Poisson transport. Equation. Okay. So again, note that you apply this equation for any path, right? This is just the way of specifying that the tensor is not changed as it is being transported along the path, regardless of which path it is, right? Now, when you look at that, right, you won't be surprised to see that this equation closely resembles the geodesic equation, actually, right? If we look at this equation, for example, partly transporting a vector, right? And remember, it's not coincidence. It may look very similar to the geodesic equation, and it's not a coincidence, of course, because remember when we spoke about the geodesic, right? We defined the geodesic as the path that parallel transports its own tangent vector, right? We said that. So what is the tangent vector to the path x mu of lambda? Geodesic is 10 parallel transports its own tangent vector. Now, do you see that? I said it last time. Right, we have 2 points. Right, and the geodesic will be the shortest path, but we can also think of it as we take the vector which is parallel to its own tangent, parallel to the path, and when we parallel transport it, it still stays tangent to the path. So it still stays parallel to itself. Right? Now, what is the tangent vector to the path x mu lambda?
The gradient.
Vector to x mu lambda, right? Is just dx mu over the lambda. Right? Guys, this is lambda. Right? This is the coordinates. x1, x2. Right? It's the x mu over the lambda. So if I plug in here, rather than v, right, I plug in x mu over the lambda, dx mu over the lambda, what do I get?
The geodesic equation.
That's the equation. Surprise, surprise. All right? Here's v mu, dx mu over the lambda. And what's in here is the geodesic. Yeah? All connects? All make sense? If it doesn't make sense to you, that means that you missed something on the way. So stop and review the material until you realize what you missed. Okay? Yeah. Now, okay, now it's time to define the curvature finally. Any idea how am I going to define a curvature? How do I know? Give me a way. Think of a way of how do I know without leaving the space that I'm in that that it is flat or curved? What can I do to tell?
Choose two passes and check whether the parallel transport is the same.
Exactly. Thank you. You got it. You got it. Right. So the curvature is defined by a quantity, it's a tensorial quantity, which is known as the Riemann tensor. Another name is the curvature tensor. There is a Riemann tensor. It's also known as the curvature tensor. I might just mix the terms without even noticing. Okay. As I'm going to show you, I'm going to prove it to you. It's going to be derived from the affine connection. And again, that's actually kind of interesting because it is going to be derived from the affine connection. And the affine connection, to remind you, is derived from the metric. So essentially, everything, all the information there is, comes from the metric. The metric, in fact, contains all the information about the space. When we speak about the physics, we'll see that it contains also, well, we already seen that it's, you can associate the metric with the gravitational potential. So it actually contains a lot of physics as well, but we'll discuss that due time. So yeah, so the way to see a curvature is essentially by taking a loop, right, between P and Q, right? So taking two passes from P to Q and back, parallel transporting a vector from P to Q, and seeing when we come back if we got the same vector after being parallel transported, then the space is flat, and if we don't see the same vector, then the space must not be flat. Right, we take a vector, I do parallel transport. When I come back, I compare. If I get this, the same result, it's flat. If it's not the same result, it's not flat. Of course, we're talking about 2 points that are infinitesimally close to each other. I'm not going to go to the North Pole. Now, of course, in Minkowski space, right, everything is going to be zero, and the mathematical way of seeing that is that the G mu nu is going to be exactly equal to eta mu nu, and so all the affine connections are going to get to be zero. All the components of the affine connection, of course, all the derivatives of the affine connection are going to be zero, so nothing is going to change, and then we say that the space is flat. Now. Anything I missed here? No. Okay, now the important thing is that the change is going to depend, of course, on the size of the loop we're going to choose. So that's the reason why we're choosing infinitesimally small loop. And in fact, what I'm going to do, I'm not going to do it like that, like I just plotted. I'm going to do it in a simpler way, or actually, it's not simpler. It's the same amount of complexity, it's just faster. So what we're going to do is, again, we're going to parallel transport the definition, or the definition, I can say. So to compute the curvature, we take 2 points infinitesimally close. Infinitesimally close. And what do I mean? I take a vector, take a vector, I call it B sigma, right? And the loop I'm going to define, so I'm going to take 2 more vectors, which will define the directions. Remember that vector is a directional derivative. It's, and transport it around a loop defined by 2 vectors, a mu and b mu. So we start from a 0, 0. Then we have a vector a mu. We have a second vector b mu. Now we're taking an infinitesimal path. So we just go to point here, which will be delta A and 0. We just went along here. And here, of course, it's going to be just increasing it, so it'll be easier for me to write. B is 0 and delta B, or just delta B. Right? And then I'm going to take, so I took my vector V along, right? So it's V sigma, right? Took it along this path. And from here, I'm going to take it now along the delta B direction. So delta A, delta B. So along the B mu. And then, of course, I can go backward. Actually, what I'm going to do, I'm going to go forward along the second path. A mu. So what I'm going to do, I'm going to go, so the 2 options are either that I go from 0, 0 along A nu, then along B nu, and then backward minus A nu and minus B nu will take me back to the original point, right? Or I can do going from point 0, 0 to delta A, delta B along this path, and then along this path and compare the 2 results, which is the easiest. Now, before I'm going to do that, note generally, right? The parallel transport, the way important ways is defined is in a way that is independent on the coordinates, right? So, you know, there should be some tensor that that tells us how the vector changes when it comes back to the original point, because we want it to be done in a way which is independent on coordinates. That's one thing. And since we're talking about small change, right, that means that it must be some sort of a linear transformation of the components of the vector. Now, being a linear transformation, that means that this tensor has to have some upper index and a lower index, right? So for, when we speak about delta V rho should be proportional to what? Should be delta A times delta B, right? Times the vector itself, V mu, or V sigma, sorry, I'm going to use V sigma, right? And then we have this tensor, which must have some upper and lower index, so it will be a rho sigma. And then it, of course, depends on the 2 vectors, A mu, B mu, but since we want to have a coordinate independent way, then this tensor should have a mu and nu to lower indexes. Right? so that we should be able to contract these two vectors. Now, just by looking at the picture, right, one thing which we can immediately tell about this tensor is that it has to be anti-symmetric with respect to exchange of mu and nu, right? R rho sigma mu nu is minus R rho sigma mu nu. Why? R stands for Riemann, of course. Why is that?
Because you can change it, you can go the other way around in the path. It should be the same.
Right? Because I can go either in this direction, or of course in the opposite direction. And if I go in the opposite direction, I get the minus sign. Okay, so we get for free one property of this tensor. Okay, again, do you see the logic of what we're doing here? Right. I argue that the action, this curvature has to be described by a tensor, right? Because I chose, a path that I chose contains two vectors, which I chose arbitrarily, A mu and B mu. Right? I only said that they have to be not the same. Right? If it's in the same direction, and obviously from the anti-symmetry part, you get a zero. Of course, right? And they have to contain, two different directions. But of course, the action of parallel transport should be independent on the coordinate which I chose, which are arbitrary. And so this tensor must have two lower indices to contract these vectors. Right now, because it's a small change, because I'm doing infinitesimal transformation, again, remember, the spaces that we work in don't have any spikes or anything which looks strange, right? Then it must have some upper and one lower index so that the change in the vector, right, delta V rho, we'll have a linear in V sigma. Okay, now we said it's anti-symmetric, that's quite clear. So this is the expression that we'd expect to get. Right, so this is the expression we expect. And this tensor here, this is the Riemann tensor. This is the Riemann tensor. Or the curvature tensor. Now it has a 4 indices, 1 upper and 3 lower. Okay, so the way to get the curvature tensor is to perform exactly what we did, doing the parallel transport along the path of a given vector. But what I'm going to do, I'm going to do something which is slightly different. Again, I'm going to take the commutator of the two covariant derivatives of parallel transports around first here and here, around this path A, and then around the second path B. So I'm going to take, let's just draw it again. So this is 0.00, right? I'm going to take delta mu, and then delta nu. And here I'm going to have delta nu and delta and nabla, sorry. Nabla nu and nabla mu. Right, the covariant derivative in the nu direction, then the covariant derivative in the nu direction. And then subtract. Now it should be quite obvious of why taking that is exactly equivalent of taking the full loop. Right? The covariant derivative tells me exactly how the vector changed when I go along this path. Right? So the commutator of the covariant derivative really tells how the vector changed when it's a difference between the change of the vectors when it went through path A and as it went through path B. So it's a really straightforward calculation. So I start with a vector which I call 0. So the commutator that's delta mu, nabla mu minus nabla mu, nabla mu. Measures the difference between parallel transporting the tensor via path A and via path. So the calculation is again pretty much straightforward. So if we take the first derivatives, the variant derivatives, so we have the nabla mu of nabla mu v rho, or just v rho semicolon mu semicolon mu. And this is nabla mu v rho v x mu plus gamma rho mu sigma v sigma. Right? You're all familiar with that? So again, this is a 1-1 tensor. So now we have to have another extra component with a minus. So we have d over dx mu of dv rho over dx mu plus gamma rho mu sigma v sigma. Now it's a 1-1, so we have plus 1 gamma. So gamma rho mu sigma will be now a dv sigma over dx mu plus what we had previously, just with the sigma now becomes a dummy. So gamma sigma mu is lambda v lambda. I'm sorry, I had to switch signs, right? This was a sigma here, which turned into a lambda here. Now we have this extra minus, so it's a minus gamma lambda mu d0 over dx lambda plus gamma rho lambda sigma v sigma. That would look particularly beautiful. So now we can go on. So this is dx mu, so just d mu v rho. At this point, I think you start appreciating this shortened notation. Plus, we have a d mu gamma rho mu sigma. V sigma, that's the second term. Right now, we have this derivative, so plus gamma rho mu sigma d mu v sigma. And now we have this, okay, it's just open the parentheses, so gamma will u sigma dv sigma will be x. V sigma v new v sigma. Okay. And this one will be plus gamma rho mu sigma gamma sigma mu lambda big lambda, and then minus gamma lambda mu and d lambda v rho minus gamma lambda mu gamma rho lambda sigma v sigma. Okay, it's annoying, but it's just algebra, right? Just algebra and just following the rules. Now, this was one, derivative of a derivative, right? Derivative of v rho with respect to mu, and then with respect to mu. Now, of course, we need to take the commutator. So we now need to subtract a similar expression with mu and mu exchange. All right. Now that's actually quite cool, because when we do this subtraction, let's see, we have this term minus the same term with mu and mu exchange, so this cancels out. We have this term and this term, and both would cancel out because mu and mu, the affine connection is symmetric with respect to mu and mu, so these two will cancel out. That's quite cool. And we have also this term and this term, which do not cancel out by themselves, but when we subtract, with mu and mu exchange, they will cancel each other, right? We'll have a gamma rho mu sigma d mu v sigma plus gamma rho mu sigma d mu v sigma minus gamma rho mu sigma d mu v sigma minus gamma rho mu sigma d mu v sigma, and then this guy will cancel this guy, and that guy will cancel with that guy. So these two guys also cancel out. So maybe it's not be as bad as it looks. And so what we're left with is that when we look at the commutator, we have nabla mu commuting with nabla mu. V rho is d mu, it's here, right? D mu gamma rho mu sigma minus d mu gamma rho mu sigma. And now we have these two gamma terms, right? Plus gamma rho mu. What are we going to do here? I changed with the sigma. I wanted to put the sigma under this, so I just use a different, just exchange sigma and rho and lambda. Mu lambda gamma lambda mu sigma minus gamma rho mu lambda gamma lambda mu sigma multiplied by v sigma. Okay, now there is something quite interesting here that happens, right? Because when you look at this expression, this is clearly a tensor. I used only tensorial quantities, so I end up with a tensor. There is no question. Right? But here, that doesn't look at all like a tensor. In fact, none of the terms here is a tensorial term, right? But somehow, miraculously, there is a conspiracy here that when you add up all these terms together, you do end up with a tensor. Right? And so this is actually a tensor because it has to be, because what we have here on the left-hand side is a tensor. And so this also must be a tensor. So we can write down nabla mu, nabla mu. 0 is R rho sigma mu mu V sigma. And R is the Riemann tensor. It is defined as equal to d mu gamma rho. Exactly what's in here. Mu sigma minus d mu gamma rho mu sigma plus gamma rho mu lambda gamma lambda mu sigma minus gamma rho mu lambda gamma lambda mu sigma. That is called the Riemann tensor. Okay. Questions?
Yeah, it feels like we go deeper in the metric. Like we start with the metrics, and then we define the affine connection, which is related by a derivative, and then we define the Riemann metric, the Riemann tensor, which is defined by another derivative plus some affine connection, which I guess make it a tensor.
So far, everything stays there. What's
Right.
the question then?
No, just to make it, you know, to organize it in my brain.
Yeah, no, you're right.
Okay.
So again, the way I derived it, right, I just took the difference, I just took the commutator, right, between the difference between the covariant derivative in one direction and the other direction. If you were to go through the same path that I suggested previously, you'd end up getting the same result. Obviously, I'm not going to prove it to you. Either trust me or derive it yourself, or look at the textbook by Wald, which I normally don't recommend because it's harder for first course in general relativity. Right. Right. The other thing which you basically noted, I mean, this looks like the commutator looks like a differential operator, but it end up that the operation of this differential operator on any specific vector, right, or any vector field, it doesn't matter, has the action of multiplying it. But essentially that's what the Riemann tensor is exactly constructed to do. Now, again, I already said this is everything here. Each term individually in the right-hand side is not a tensorial quantity. But again, miraculously, they all conspire that when you add them up like that, you do get a tensor. And yeah, and from the definition here of the Riemann tensor, it's obvious that it's antisymmetric in exchange of mu and mu, right? R rho sigma mu minus R rho sigma mu. It's pretty obvious, right? Just exchange mu and mu, and you get this extra minus sign. That's pretty straightforward. And the other thing which you noted rightfully, we're messing up things in some interesting way, right? We started with the metric tensor. We took the first derivative, plus some extra manipulations, and we got the affine connection. And then we took the affine connection and we took the derivative of the affine connection as well, plus some extra messy parts, and we ended up with the Riemann tensor. So the metric tensor is in fact constructed from the metric tensor and the first and the second derivative of the metric tensor. Right? The Riemann tensor is constructed from the metric, its first and second derivative. Just to conclude this part, I would say that, of course, we can look at the action of the Riemann tensor on any arbitrary ranked tensor, not necessarily just a vector. Okay, right? So if you look at the commutation of the covariant derivatives, so generalization, if we look at the computation of the covariant derivative, nabla rho and nabla sigma on x, mu1, mu k, mu1, mu l, right? X is any tensor, right? Then you know what we're going to get, or you can guess what we're going to get, right? We're going to get the Riemann tensor, and the upper index, right, will be the, all the indices one by one, right? All the indices one by one. Then two lower indices are the indices that we're using. Here will be rho and sigma, and then the third one will be a dummy index, which will replace what we have in the tensor x, right? So let me write this t. It's the tensor t. So this will be equal to r mu1 and then lambda rho sigma t lambda mu2 mu k mu1 mu l plus r mu2 lambda rho sigma t mu1 lambda mu3 mu k mu1 mu l. And then for all the lower indices, then of course we're going to get it. The dummy index will go up, so it will be r lambda, and then the lower indices will be one of the lower indices, so it will be a mu1, and then the rho sigma doesn't change. Of course, the t mu1 mu k, and then the lambda mu2 mu l minus r lambda mu mu l, and then t mu1 mu k mu1 mu2 mu l minus 1 and 1. Right? Yeah.
After the new L, it's a rho sigma in the final Riemann tensor?
Thank you. And specifically, if you look at the commutation of the covariant vector, nabla rho, nabla sigma of v mu will just be a minus r lambda mu rho sigma v lambda. So again, if the curvature tensor vanishes, then the covariant derivatives commute. Right? If the curvature tensor vanishes, the covariant derivatives commute. Right. Now there is a theorem, the theorem that we were after, right? Which connects the Riemann tensor and the curvature of space. Right? So Riemann tensor and the curvature of space. So this is essentially what will enable us to define what do we mean by flat space versus curved space. And can anybody guess? What am I going to say? Okay, well, a necessary and sufficient condition for the metric G mu nu to be equivalent to a Minkowski metric eta mu nu would be what? Actually for the metric G mu nu, that's to be equivalent to the metric to the Minkowski metric. Eta mu nu. You know, I asked you in the problem set, right, to find the transformation. I gave you some metric and I told you this is in fact a flat metric, right? And what you needed to do was to simply give the transformation, which will, you know, change the coordinates, you know, from x to psi, right? So there is a transformation. X to psi, right? That exists. So what are the conditions? You don't need to guess very widely. Come on, guys. Very wild guess.
No, maybe it should be diagonal, first of all.
Metric is not necessarily diagonal.
No, but
how do I know that something is flat, guys? What have we been talking about all this lecture? How do we know that the metric is flat?
the R is 0.
Thank you. Right. So we really have two conditions, right? One is that the components of the Riemann tensor, the components of the curvature tensor vanish everywhere. Right. And the second one, which is a bit more tricky to get, is that the metric G mu nu has 3 positive and 1 negative eigenvalues. right? Okay, that's me. So now you know, I give you some metric, can be very strange, strangely looking, but it can just be some manipulation that I did, right? Of taking a flat space and writing it in some coordinates that I invented, right? Could be spherical, could be cylindrical, right? Spherical coordinate does not change the space. It just change the way I describe the space, right? So if you're given a metric, then you can tell immediately, well, not immediately, you need to go through this calculation, right? Calculate the Riemann tensor. And if you see that the Riemann tensor vanishes everywhere, then, you know, it's really just a matter of complicating your life because the metric is really flat, right? Pretty straightforward. To be equivalent to a Lorentzian or Minkowskian metric, then it has to have 3 positive and 1 negative eigenvalues. Now, one way is really straightforward to show, right? So the necessary, so one way necessary. This is something which I can do right away. It takes a few seconds to do, right? So if we have some coordinate system such that if there is a coordinate system such that d sigma g mu is equal to 0, right, that automatically means that gamma rho mu sigma mu is equal to 0, and so all the derivative, right, d sigma gamma rho mu is equal to 0. So automatically R rho sigma mu will be equal to 0. Right? But this is a tensorial equation, right? So if this is a tensorial equation, if this is true in one frame, it's true in any frame, right? So the requirement that the Riemann tensor is vanishes is necessary condition for the metric to be flat, or the components of G be constant everywhere. So or equal to 0, necessary condition for the components of G mu to be constant everywhere. Now, sufficient condition this is a much more difficult way of showing that, the opposite. Okay, I gave a sketch in my notes about how to do it, but it's not a full derivative because that requires a little bit more of math, which there really is no point in getting into because except from this proof, it doesn't give you too much. So I would just leave it. Say that there is a theorem which is called Frobenius theorem. Which shows that if the commutator vanishes, then you can find some coordinate system which will fulfill the required conditions that we have. It doesn't, the proof for that appears in the book, not the textbook, the textbook by Schutz, but not the textbook that is used to teach this course, but another textbook on more advanced math. It's called geometrical methods. It's called. So proof by shoots. So geometrical methods. So I'm not going to get into that because there's just I don't think it's going to give us much. Bottom line. So I just take it that either you trust me or you go to this textbook and you can read it there. I'm not giving you the full proof because it will just be some subtle things which I might get confusing and you might get confusing as well. So we're not going to get too much. All right. But this is essentially what I wanted to get. Right. The necessary and sufficient condition for the metric to be equivalent to Minkowski or flat metric is just that the curvature tensor vanishes everywhere. And the second condition is that the metric has 3 positive and 1 negative eigenvalues. All right. Questions? Any questions? No, this is your time. Okay, so I think it's a good place to stop here. What we're going to do on Sunday is we're going to further study the properties of the Riemann tensor. It has some very interesting properties, which obviously are going to find out to be quite useful for our purposes. And yeah, we'll study that, and then a few more small things which kind of completing the picture. And then I think we'll have all the tools, or nearly all the tools we need to go and study Einstein's field equation. Any further questions or comments?
I have something to talk to you about, not about the lecture. So after.
After the lecture, okay. I'm going to post the next problem set today. We'll get a week. Again, if you find any troubles, call me, contact me, and I'll answer. Some of you do it, and you know that I answer you. Have to check out what happens with the grading, because there is somebody who grades your homework, and you need to talk to her and see where things are. Okay. All right. Any more? If not, then I'll stop the recording.